alternative to mandatory standards and can be based on self-assessment or benchmarking. Best practice is a feature of accredited management standards such as ISO 9000 and ISO 14001. So what is best practice? A best practice is a method or technique that has been generally accepted as superior to any alternatives because it produces results that are superior to those achieved by other means. Okay, I have a... The mill certificate is checked to ensure the material received complies with the purchase specifications. After the material has been confirmed to comply with the purchase specifications, the material should be correctly identified and stored. Sometimes marking can take a few attempts to get the identification correct. But this process should already be established in the company's quality management program. When working with different materials, it is very important to reduce contamination between material types. It is already a well-known best practice to segregate carbon steel and aluminium to prevent rust staining from carbon steel grinding dust and localized corrosion. Another less known best practice is to also segregate carbon steel aluminium as aluminium grinding dust combined with carbon steel grinding dust, which can contain iron oxide from removing rust, can create thermite, which is explosive. The Aluminium Association has guidelines for the safe handling of aluminium fines, such as grinding dust, during fabrication operations to prevent fire and explosion risks. Another best practice is to ensure the correct material-specific grinding discs are used for each type of material being processed, and that the grinding discs are not interchanged. This is a common best practice for stainless steel and carbon steel, and should also be adopted as a best practice for aluminium and carbon steel also. Everybody seems to know that carbon steel and stainless steel needs to be segregated. Not many people understand the need to also segregate aluminium from carbon steel. So let's have a look at cutting and preparation of materials. There are many different types of cutting methods available, which range from handheld systems to mechanized systems. The cutting methods available can include oxy-fuel, plasma, and abrasive saw systems. All cutting systems will have their own best practice principles developed from many years of workplace experience. So let's look at some best practice principles for oxy-fuel welding. So oxy-fuel is very commonly used, and there are many best practice principles that should always be followed to ensure safety is optimized. I'd like to highlight two that are specific for oxy-fuel cutting and welding. Acetylene cylinders should always be standing. Storing or using an acetylene cylinder on its side is not recommended, as acetylene cylinders contain liquid. Acetylene cylinders, both full and empty, should always be standing. If an acetylene cylinder has tipped over or is stored on its side, the cylinder should be placed upright and not used until the liquid has settled to the bottom. The best practice rule is to wait at least 1 hour before using the acetylene cylinder. A flashback can easily occur for many reasons that include worn tips, incorrect gas pressures, faulty equipment, slag blocking the tip hitting the workpiece, and many more. When a flashback occurs, the ignition of the oxy-fuel occurs inside the mixing chamber of the oxy-fuel torch and can travel back through the hoses to the cylinder faster than someone could get to the cylinder to close the cylinder valve. So flashback arresters provide protection from a highly explosive situation that can lead to a large amount of damage and personal injury. This is an example of a damaged regulator where you can't see the acetylene pressure that's being used. Acetylene also has defined draw-off rates, because if you exceed the draw-off rate for acetylene, then it is possible to draw the liquid from the cylinder, which makes acetylene unstable. Typically for site work, they would use an alternative oxy-fuel, an alternative fuel gas, which is much safer. And also flashback arresters, very important. You don't know when a flashback will happen. Another best practice is preventing rust on prepared joints. So best practice will always require all foreign matter such as grease, paint, oil, rust, and heavy mill scale to be removed before welding. Steel plates are usually cut, beveled, and stored waiting to be used. RP6 is a proprietary oil-based rust preventative fluid that will keep ferrous metals clean and corrosion-free with indoor protection for up to 6 months without affecting weld quality. RP6 can be applied by spray, dip, or brush, and increases productivity by eliminating the need for grinding, shot blasting, or chemical cleaning the joint before welding. And these are some examples. This plate on the left, this has been treated with RP6 and left outside in the same environment as this plate on the right, where you can see the rust. This is a plate in a fab shop that's been left outside. You can see the heavy corrosion here and the amount of rust. So ideally, all joints should be clean, rust-free, free of mill scale before welding. If you do try to weld over rust or oil, the typical defect is porosity. Correct alignment and good fit up is essential for high quality welds. Best practice should encourage the use of fixturing tools to enable precise assembling of components. Magnetic type tools are very easy to use and now have switchable magnets that make locating the parts and removal of the magnet fixturing tool very easy. There are electric type and manual magnetic hand lifting tools available that can lift up to 27 kilograms. So these are some examples of using a fixturing tool to get the correct alignment of parts and also for easier handling of parts. So let's have a look at consumable products. These are storage recommendations from Lincoln Electric Europe. The recommendation for controlled storage conditions are 50% or less relative humidity when the storage temperature is between 27 to 37 degrees C. So what is relative humidity? Relative humidity refers to how much water vapor is in the air compared to how much water vapor the air could hold at the same temperature. So a relative humidity of 50% means the air is holding half the water vapor. The best way to control humidity is to use a dehumidifier. If a dehumidifier is not available, the preference is to use heating rather than cooling to reduce relative humidity. This one is really interesting because a lot of times when you visit controlled environment storage, it's usually cooled because for some reason, especially in the tropics, people use air conditioning or cooling to reduce humidity. So while you don't feel sticky, it's not actually reducing the relative humidity. So when you heat the air will expand and increase its ability to hold moisture, which causes the relative humidity to drop. So this is why we recommend using heating to control the relative humidity in your controlled environment storage. If you use cooling, the relative humidity will increase as the temperature drops. This is because colder air requires less moisture to become saturated. So best practice for consumable storage is to follow the manufacturer's recommendations. If the relative humidity needs to be reduced, it is done more easily by heating. And this is some examples from a website showing you the temperature, the dew point, and the relative humidity. So in this case, if it's 35 degrees, our dew point's 30 degrees, then our relative humidity is 75%. Now, if we use cooling and we reduce the air temperature to 30 degrees with the same dew point, then our relative humidity is actually 100%. We've completely saturated the air. But if you increase the temperature, so now we're expanding the air. So we've increased the temperature to 43 degrees, dew point still the same, but now our relative humidity has dropped to 49%. So to maintain low hydrogen properties, a lot of electrodes used for low alloy steels, higher strength materials require low hydrogen properties. And the reason for that is that as the strength of a steel increases, you need less hydrogen to create a crack. So to maintain low hydrogen properties, electrodes may require redrying depending on the type of electrode, packaging, and storage conditions. Best practice is to follow the manufacturer's recommendations with special attention to the temperature, holding time, thickness of electrode layers, and the number of times redrying can be done. Redrying information is usually provided in product information available on manufacturer websites. So here we have some examples. This is a basic low hydrogen type electrode. The redrying time is 2 to 6 hours. This is the recommended temperatures, so 250 to 375 degrees C. And then this is the information for the holding oven. So holding is different to redrying. Redrying is done at a much higher temperature, and that is to remove the moisture from the electrode coating. Holding is done after redrying, and that is to maintain the moisture level in the electrode coating. So the times when you would redry an electrode is if you've received electrodes that are in non-hermetically sealed packaging, so that would be a cardboard box where moisture can be absorbed by the flux coating, or if the electrodes have become obviously wet, somebody's left them out in the rain, dropped them in a puddle of water. So this is the Hydroguard range of ovens designed to hold up to 160 kilograms of electrode. It's unique in the circular design, distributes heat more evenly, and directs moisture to the adjustable vent at the top of the door. That's here. This is the vent. Temperature is adjustable from 38 to 228 degrees C, and an indicator light shows active heating. There's also a portable rod oven, so the temperature is preset at 150 degrees, and there is a power on indicator lights for easy visual confirmation by the welder that the portable rod oven is working. Another option for maintaining the quality of low hydrogen electrodes is to always store low hydrogen electrodes in a holding oven. However, depending on the location of the project, sometimes using vacuum-packed electrodes is easier to control and can also be more cost-effective than having re-drying and holding ovens. Sahara Ready-Pack electrodes are supplied in 2-kilogram packets and has a label designed for a welder to add their name, date, and time of use information. That's these 3 rectangles here. Provided the original vacuum seal is present and the packaging is undamaged, the electrodes can be used in the as-received condition direct from the packaging within a period of 8 hours after opening in 35 degrees C temperatures with 90% relative humidity, with the electrodes remaining in the open packaging and protected against excessive conditions as condensation, rain, or water damage. Now let's look at equipment. Best practice for equipment is to conduct routine maintenance. And routine maintenance is specified in the operator's manual supplied with the equipment and typically requires removing the side panels and cleaning the machine with low pressure compressed air. Some machines with additional functions such as VRD, which is a voltage reduction device used with stick electrode or SMAW welding for increased safety, will require additional routine maintenance for checking the VRD status lights every day or every shift. Newer equipment is designed for easy maintenance. The PowerWave ACDC 1000 SD Submerged Arc Welding power source is supplied standard with a washable stainless steel filter for the cooling air, which can be removed without undoing any screws. The back of the machine opens like a drawer by removing 4 screws, 2 on each side. The new pipe fab welding system, the side panels of the power source can be removed by undoing 4 screws. These are all new design features to make best practice maintenance of equipment much easier. And some wire feeders, as we saw in this video, are also designed to be completely disassembled in 2 minutes. When conducting routine maintenance on power sources, the wire feeders and welding guns should also be checked. Wire feeder drive roll systems and welding gun liners can also be blown out using compressed air to remove any buildup of dust or wire shavings. This will reduce the risk of contamination of the wire and ensure good wire feeding for stable arc performance. So here's a wire feeder. You can see the amount of dust and wire shavings that have collected around the drive rolls. This arrow indicates the direction of the wire feed, and you can see here on the outgoing bushing that there's a very big buildup of particles. So this wire feeder needs a bit more maintenance. When setting up welding equipment, best practice should ensure the correct type of drive rolls are used for different wire types. Aluminium wire requires a polished U-groove type drive roll and Teflon wire guides. This is to prevent contamination and deformation of the wire. V-groove drive rolls are used for solid type wires for carbon steel or stainless steel MIG or GMAW welding. Knurled type drive rolls are used for flux cord wires to provide better grip. It is also important to ensure the correct size wire guides to properly support the wire during feeding to prevent the wire from surging or jamming. Best practice should also be followed to ensure the correct drive roll pressures are set. If the tension adjustment is not calibrated, the best practice guideline is to adjust the drive roll pressure so that when you're holding the wire at the wire reel side and you feed the wire, the wire will continue feeding, but if you hold the wire at the contact tip end, it's possible for the wire to slip in the drive rolls. That way, if there's a bad arc strike, the wire is not going to bird's nest or become stuck in the drive rolls. A best practice principle of checking the contact tip before adjusting drive roll tension is recommended, as many welders will automatically increase drive roll tension whenever there is a feeding problem. If the drive roll tension is increased, it is possible to squash the wire, which makes the wire more difficult to feed, as the wire will jam in the tip. So sometimes when there's a wire feeding problem, increasing the drive roll pressure actually makes the problem worse. If the wire is not feeding smoothly, the items to check are the welding gun does not have sharp bends, and the contact tip, as contact tips can shrink due to heating and cooling cycles during welding, and this will cause wire feeding problems. So every time you weld, the contact tip will expand, and then when you cool, the contact tip will shrink or contract again, and then sometimes it will actually shrink, and then it starts to bind on the wire. So if you see that your contact tip is changing from a nice copper color to a dark purple or even black color, then the contact tip is overheating, and chances are it's going to shrink, and that will give you wire feeding problems. The easiest method of checking the contact tip is to remove the contact tip and check the wire feeding. So when you change a wire reel, it's always recommended as a best practice to remove the contact tip before feeding the new wire. This allows you to check the contact tip for wear and also to replace it if necessary. And it also makes feeding the wire through the welding gun a lot easier. So remove the tip, check the tip to see if it's badly worn, feed the wire through your welding gun, and then reinstall the tip. So this picture here is showing, this is a 4mm wire used for submerged arc welding. So you can see the amount of wear in the contact tip. And the reason why the contact tip is very important is because the current transfers, that's the welding current from the power source, transfers to the electrode or the wire at the contact tip. That's why it's called a contact tip. So if you have bad contact because the wire can move in this elongated hole, then that's going to affect the transfer of the welding current and give you an erratic arc. So when you have a worn contact tip, it can give you an unstable arc, and it can also allow the wire to wander because the wire is feeding off a reel, so it has a natural curve in it, and sometimes the wire can create circles. So this is the Lincoln Electric Magnum Pro system. The welding guns are available in air-cooled, water-cooled, and also push-pull type systems. Push-pull guns are very popular for longer distances using aluminium because aluminium wires are very soft. So there's a push motor that's in the wire feeder at the power source, and then inside the welding gun, in the handle, there's another set of drive rolls which pull the wire, and that keeps the wire in constant tension so it doesn't bird's nest or kink in the liner. This is a self-shielded gun, so this is used for self-shielded flux cord wires where you don't need any shielding gas. All of these different products use common parts, and it's also possible to get a flexible neck to give you better access into restricted joints. So let's have a look at connections. So poor connections can be connections that are too small or welding cables that are too small. They can also be bolted connections that have come loose or weren't tightened properly. Poor connections are good at low amps, but at high amps like welding, the poor connections can block the flow of welding current and will start to become hot. As the pore connections become hot, they can sometimes start to become red from the heat and smoke. It's also possible to see sparks when high currents are being used. Typically, you will see discolored connections, bolts and nuts, or hard or crumbling or melted insulation. Anytime there is heat in a welding circuit, the heat indicates there is resistance. And when there is resistance, this will affect the voltage, which is the arc length of the welding process. As can be seen in these pictures, a bolt has been fully welded to a steel plate with a good bolted connection. However, the current path is through a small tack weld, which will become hot and create an area of resistance. In this picture, the cable lug has been tack welded to a gantry rail. So this is the lug. So all of your return path for your welding current is going through this small little tack weld. This is an example at low amps. Everything flows nicely, but at higher amps, where there's a poor connection, you'll end up with a localized heating effect, and with electrical circuits, anytime you have heat, that indicates resistance, and resistance will affect the welding voltage. And that's important because when you change the welding voltage, it can change your transfer mode. So what you expect to be using, you don't actually have. And this is a video that's showing a poor connection that's heating up. So as the welding's happening there, you can see that bolted connection is getting extremely hot, and that's affecting the welding and giving you a bad arc. Another example of poor connections. This machine is a 1000 amp welding machine, which has a cover to protect the welding output connections. So during a worksite visit, I noticed that one of the welding cables was not routed through the strain relief that protects the output stud from being damaged when people pull on the welding cables. So when I opened the output stud cover to reroute the welding cable, I found that the welding cables did not have any cable lugs and were twisted around the output studs. The best practice to learn from this: route cables correctly to reduce possible damage, and always use cable lugs and ensure connections are tight. Losing voltage through undersized cables or poor connections increases with the heat buildup in the cable and connections. This can often make it appear that the machine is suffering from a thermal problem, or maybe there are issues with input power voltage fluctuations, which will result in the machine being taken out of service and sent to maintenance for checking, but the machine is operating correctly. Welding cable size is dependent on the amps being used and the total combined length of the electrode and work cables. Welding cables have traditionally always been made from copper, but aluminium cables are now available and are very popular due to the light weight. Some aluminium cables are also copper colored and have the appearance of being copper, but are very light. So when you pick up a 100-meter coil of cable, if it's 35 millimeters squared and you can pick that up, chances are it's aluminium, because copper is much heavier than aluminium. The problem with aluminium cables is that aluminium will melt while copper cables will discolor. So if you overheat an aluminium welding cable, it will get to a point where the aluminium will melt. With copper won't melt, but what will happen is it will discolor, and you'll most probably see the cable cover starting to smoke. So different cable suppliers will also have different sizes of cable. Ideally, the cable size should be specified by the area of the conductor not the area of the cable insulation. As seen in the pictures, the 95mm squared cable on the left has less conductor than the 75mm squared cable on the right. Even though the insulation is bigger, which makes the cable look bigger, the amount of conductor to carry the welding current is smaller. An undersized welding cable will become hot, which indicates there is resistance, and anytime there is resistance or heat in a welding circuit, this will affect the voltage, which is the arc length. So here we can see the width of the cable is 17mm, but the conductor is 11mm, and that's compared to 12mm. And this is a smaller size cable, 70mm squared. And this table is showing the size of welding cable to use for the welding current and the combined length of the cables. So as you increase the welding current and you have longer distances, then you need to use larger cables, and sometimes you need to use multiple cables. So for work cable connections, try to avoid rotary clamps. Rotary clamps are typically used for circumferential welding. However, they have a lot of problems. If they're not lubricated properly, they stop turning, and then the welding cable winds up and creates other problems, putting stress on the cable connectors and also causing the rotary clamp to become loose or fall off. After continued use, rotary clamps become less efficient and start to heat up, as can be seen in this picture with the discolored connections. Many times the bolted clamp connections also become damaged, and the rotary clamp is then welded to the end of the pipe being welded. This picture shows a best practice of grinding the area where the rotary clamp will make contact. While the clamp is very big, sometimes the contact area can be very small, and it is limited to the size of the clamping bolt. And remember, anywhere there is heat in a cable or connection, it will affect the welding voltage. A better alternative is to use cup brushes. Brushes have been used for many years. Originally, the brush was a specially made rectangular brush. Now the use of steel cup brushes has been much more cost effective. For best practice, try to avoid the use of rotary type clamps for work cable connections. So how important is voltage? Voltage determines the arc length. So changing the voltage will affect heat input, and changing voltage can also affect the welding process transfer mode. In self-shielded flux cord arc welding, voltage can cause porosity in the weld metal and can also affect the slag formation. In this example, there was a 1 volt change in the welding procedure to go from a poor slag cover with a hole in it to a good slag cover that fully covers and protects the weld. In SMAW, so that's stick electrode welding, and flux cord wire welding that have slag, the best practice principle is there should always be a full slag cover over the weld. In self-shielded flux cord welding, a change of 1 volt can change the slag formation. Another best practice is to ensure the welders are properly trained and familiar with the techniques of the welding process being used. Gas-shielded flux cord arc welding typically uses voltages, more voltage at the same welding amps, typically around 5 volts more, and has a much longer arc length. Self-shielded flux cord wires use lower voltages and have more of a stubbing type arc characteristic. So when welders experienced with using gas-shielded flux cord wires change to using a self-shielded wire, they will usually increase the voltage to make a smoother arc similar to a gas-shielded flux cord wire. However, the higher voltage can produce porosity in the weld metal, which is a common problem when welders change process but are not trained. So the best practice principles: ensure welders are correctly trained for the processes they are using. Ensure connections are tight and welding cables are the correct size to reduce heat buildup, which will affect arc voltage. We've looked at the effects of having poor connections or incorrectly sized welding cables, and now the heat buildup causes resistance, which affects arc voltage. Now let's look at what happens when long welding cables are coiled. When a welding cable is coiled and placed on a hook for good housekeeping, during welding, the coiled cable creates magnetic fields like a transformer, which affects the welding amps. Depending on the length of the cable that's coiled, it is possible to lose a large amount of amps. In this video, which was done at the Lincoln Electric Advanced Solutions Center in Singapore, the magnetic field was strong enough to support 3 kilograms of steel. This picture shows a 9-inch wire brush held by the magnetic field created by the coiled welding cable. This customer was welding a cross-country pipeline and was having quality problems and failed x-rays due to poor arc performance caused by coiling the long welding cables. Changes in welding amps will affect penetration. This is an example relating to MIG welding with mixed shielding gas. Changing amps or changing volts can affect the transfer mode being used, which can affect spatter levels, penetration, and create an unstable arc. Coiled cables and poor connections can affect arc performance to the extent that the new PipeFab welding system has cable view technology to warn when the inductance in the welding system becomes excessive to ensure the best arc performance is always available. And we'll show this warning message, which has a recommendation to uncoil, unwind any coiled welding cables, and or shorten cable lengths. So when you have poor connections or small welding cables, anything that becomes hot, that will affect your voltage. So anything that becomes hot indicates resistance. When you have a coiled welding cable that is creating a magnetic field, that affects inductance. So that's the differences. Inductance affects your welding amps, resistance affects your welding voltage. The best practice solution for long cables is to use cable connectors. This allows the correct cable length to be used and also allows the extra unneeded cable to be stored and protected from damage. So rather than coiling the cable, use these cable connectors and you can remove unwanted sections of cable. So let's look at some best practices related to welding processes. A best practice used for TIG welding is to change the standard collet and collet body to a gas lens type. The gas lens provide a better shielding gas flow as shown in the picture, which provides better protection for materials that are highly sensitive to atmospheric contamination like titanium, stainless steel, and aluminium. Using a gas lens also allows the tungsten to be extended, which allows better access to joints. So a gas lens is a special type of collet body that has a very fine mesh to diffuse the gas. With a standard collet body, the diffuser holes are on the sides, and that's why you get this spiralized flow of gas. Another best practice for regulators is to ensure the correct shielding gas flow rates are being used. It's also a best practice to use heated regulators for 100% CO2 shielding gas to prevent the regulator from freezing, which will affect shielding gas flow rates. When using gas shielded flux cord wires, it's also a best practice to train welders to recognize what the arc looks like when the shielding gas flow rate is reduced or there is no shielding gas. Some welders may not realize there is a problem with the shielding gas until they remove the slag from the weld and see porosity, or sometimes the weld can still have a good surface appearance, but there will be internal porosity, which will only be found out after the joint is fully welded and final inspection is being conducted. That will become a repair and a quality issue. Also remember that regulators for argon and mixed gas shielding gases have different flow rate markings for the different types of gas. So when you look at the regulator, there's typically two scales because the gases have different densities. And this picture shows a flow meter that is full of ice because the CO2 has frozen inside the regulator. The contact tip to work distance or electrical stick out should be recorded on the PQR and specified on the WPS. This is a very important best practice as changes to contact tip to work distance or electrode stick out will affect the penetration. This can be seen in this video that shows a MIG welder changing the contact tip to work distance and the effects on the ammeter on the machine. This is due to the change in resistance created by having a longer or shorter wire extension. So here the voltage is staying the same, but you can see that the amps are changing, and that's because of the changing resistance in the wire extension. When the wire extension becomes longer, there is more resistance and the amps will decrease. So what does this mean? It means that two welders can be using the same wire feed speed but have completely different amp readings because they are using different contact tip to work distances. And this can sometimes be mistaken as being a problem with the output from the welding machine, when really it's a problem of operator training. Other factors can affect contact tip to work differences, which will affect the amps and penetration during welding, are the nozzle type. Nozzles for MIG or gas shielded flux cord arc welding are available in different diameters and different lengths. Where the contact tip can be extended past the end of the nozzle, flush, or recessed. Contact tip to work distance can also be affected by incorrect setup of the welding gun. In these examples, the insulating ring has been installed backward, which also blocks the diffuser holes in the contact tip, and that will restrict the gas flow and give possible porosity problems. But if also the contact tip will be recessed when the nozzle is fitted, as the position of the insulating ring is different. This will create a longer contact tip to work distance, which will reduce the welding amps. For best practice, ensure the correct length nozzle is used and is correctly fitted to ensure the welding parameters are correct. For some welding processes, such as the Lincoln Electric Surface Tension Transfer process, there are specific recommendations to ensure the best arc performance from the process. The surface tension transfer process uses a drag technique with the welding nozzle as shown in the video, which requires a specific size of gas nozzle, which is also dependent on the bevel design. The best practice for STT, open gap root pass welding, is to maintain a 10mm contact tip to work distance during the welding process, which is easily done by following the nozzle and bevel recommendations. Welding tools. Nozzles should be checked. Spatter buildup should be removed. This is an example where there was so much spatter on the nozzle that the contact tip welded to the spatter, and that's why the wire is still stuck here. So when the operator removed this nozzle, it also removed the contact tip, and everything is welded together. This is a spatter ring that was removed from the end of the nozzle. So spatter buildup can occur from having coiled cables or poor connections, because that's going to affect your amps. It's also good practice to cut the wire before restriking the arc, because when you stop welding with a flux cord wire, there will always be a bit of slag on the end of the wire, which is an insulator, so you won't be able to make a good arc strike. With MIG welding, the GMAW process, sometimes you'll get a big ball on the end of the wire which will oxidize. That oxidization on the wire is also an insulator, which also makes it hard to have a good arc strike. In those cases, if you don't cut the wire, what will happen is the end of the wire will blast off. Sometimes the wire will melt back onto the contact tip, meaning that you'll need to replace the contact tip. So best practice is always cut the wire before restriking, before starting your next weld. And this is a multi-tool that has a lot of very useful functions. You have a circular holder for removing contact tips, you have wire cutters, you also have a larger holder for removing the nozzles. It also has a serrated edge so you can clean the nozzle from the spatter from inside the nozzle. With submerged arc welding flux, if there's any magnetic particles in the flux, that will cause porosity, and typically people repair porosity by either gouging or grinding. In this example of a customer that was making a longitudinal weld inside a can, they had porosity, so they were grinding out the porosity. But may be difficult for you to see, but this is the coil of wire. My PowerPoint's hanging. Just wait a moment. So in the picture, in the green circle is the flux hopper. To the right side, you can see the wire reel. So the person is inside the can, grinding out the porosity, and all of the grinding dust is, well, a lot of it is going back into the flux hopper. So then what happens is you end up with more porosity. And so what they should be doing is they should be moving the column and boom further away, or completely covering the flux hopper to stop the grinding dust from going into the flux hopper. Another good practice is to always add new flux to your recycled flux, and that's to ensure consistent chemical composition in the flux. And that's because at high temperatures, any manganese and silicon in the flux burns off at higher temperatures, and it also maintains the consistency of the particle size. And the picture on the left there is showing the magnetic particles that are inside flux. So whenever you recycle flux, you should also use a magnetic separator to remove any magnetic particles, which could be grinding dust, mill scale, from the flux before it gets used again. My PowerPoint's having a go slow moment where it's thinking about whether it needs to restart or not. If anybody has questions, you're welcome to type them in the chat or the Q&A. You can also raise your hand and I can unmute you if you'd like to talk. Now let's have a look at submerged arc welding and also contact tip to work distance. So in the submerged arc process, the contact tip to work distance distance, that needs to be checked after every weld pass, because as you make a weld pass, you're putting down an additional layer, so that's typically around 3 millimeters. So your contact tip to work distance will change after every pass. And depending on your operating system, that will either affect your welding amps, which will affect your penetration, or if you have a constant current system, then it's going to affect the wire feeding speed, which will affect your deposition rates. And the general guideline for the contact tip to work distance in a submerged arc system, well, any wire system, is 8 times the wire diameter. And this is a little step gauge that Lincoln makes to help people set their contact tip to work distance. So parameter specification, this is also very, very important. So how much does wire feed speed, amps, and volts matter? A WPS is based on the PQR with an allowable parameter range based on the essential variables for the code or client specification being used for the project. When a client inspector is checking the actual welding parameters against the WPS, they will be looking for a specific range of values. And depending on the contact tip to work distance, heat in the welding circuit, or inductance from coiled welding cables, the actual values can be very different to the WPS, although the equipment is functioning correctly. So in a constant voltage system, the work points, the work point that you typically set is the wire feed speed, but a lot of times people record amps. But to be correct, the amps should be indicated as a reference, typically in brackets. And if you specify amps in a constant voltage system, this can have a very big variation because the amps will only be correct when the contact tip to work distance is correct. So for a constant voltage system, you should specify wire feed speed and volts. In a constant current type system, the parameters to specify should be the amps and the volts. Another look at submerged arc welding. This is with legacy transformer type equipment. So typically you would have a DC lead arc with an AC trail arc. It's also possible to use AC with AC welding now, using the new PowerWave AC DC submerged arc power sources, which were first sold in 2004. And in 2010, the PowerWave AC DC 1000 was upgraded to the current PowerWave AC DC 1000 SD, which is the severe duty model with these stainless steel panels. And to date, there have been over 20,000 PowerWave AC DC 1000 SD machines sold globally. And the biggest benefit of using the PowerWave DC 1000 SD is the ability to weld with variable AC square wave welding current. So this is a very common equipment setup problem that we have with legacy tandem arc welding systems. Usually the welding cable on the direct current lead arc machine is routed in from the left of the control box and out on the right, and it connects to a current shunt. But on the AC trail arc, people follow the same cable routing as the DC machine. So what happens is, when you route the welding cable in on the left and out on the right, it creates an induced voltage effect, because we're now using alternating current. So as the welding current is alternating, the gap, so the separation between the two cables, creates an induced transformer effect, and that actually gives a voltage error of up to 8 volts on this analog meter. And that's all because of cable routing. So this is incorrect. It could also make it seem like the equipment is faulty or the voltmeter is not working properly. The correct cable routing in this situation is to route the cable in and out on the same side and to keep the welding cables as close together as possible to reduce that induced transformer effect. So this is the correct method of doing that. And the interesting thing is, it's been noted in instruction manual, and this is going back to 1990, that the correct way to route the welding cables is in and out on the same side. The challenging thing is a lot of people don't read manuals. The other challenge is our manuals are in English, and not everybody, and that's not the native language for most countries in Southeast Asia. So having assistance from the principal or someone with experience to set up the equipment is very important to make sure that the equipment setup is done correctly so everything is working properly. The other important note with AC welding current is that you need to separate the input control cable. So this is a control cable that controls the functions like turning the arc on and off, inching the wire up and down. That needs to be separated from the weld cables by at least 300 millimeters to avoid induced voltages. So that's to make sure that everything works correctly. So with AC welding, the best practice is do not coil the cables, avoid steel cable trays, use plastic, ABS or open type cable trays, route the electrode and work the cables together. Sometimes you can also twist them together to make sure that they are as close together as possible. And do not route the cables inside column and booms, because then you're running a cable through a big steel tube which amplifies the induced transformer effect. So here's a setup where it's done correctly. The electrode cables are separated from the control cables, and this is using an open type cable tray. Another safety feature is to be mindful when grinding is to use safety glasses. That should always be mandatory. And when grinding, you should also use a face shield with your safety glasses. This is an example that happened to myself. I was doing a demonstration on a 6G joint. I was removing a bridge tack that was under the pipe, and as I was grinding it, I grounded a little too far, so it actually became loose. It came free, and the bridge tack was gripped by the grinding wheel and bounced off my full grind shield head shield. So this is a very good head shield. It has a full grind shield under the welding lens, and the impact from that bridge tack left these two scratches in the grind shield. So that if I was only using safety glasses without the grind shield, that would have hit me just above my safety glasses. Another type of head shield that you can use is a powered air purified respirator type. So these have a HEPA filter with a blower fan that goes on a waist belt, and these provide purified air. So the battery-powered air filter motor is worn on the waist belt. It has shoulder straps to provide additional support and can deliver between 180 to 220 litres per minute of purified air. Very comfortable, highly recommended for stainless steel, which has a lot of hexavalent chrome. Another best practice is the process of submerged arc welding uses a continuous wire electrode. But with grinding and gouging, poor grinding gouging can affect joint access, causing slag inclusions. So this is an example where a lot of times when people grind, what they will do is they will take the grinding wheel and they will just go straight into the joint, creating this big sort of U-grooves. So what happens here is, as you weld this, you end up with slag inclusions in the bottom because the arc cannot reach to the bottom of the joint. And that's what this is showing. So if you make a very narrow type grind, then you'll end up with a slag inclusion. The correct method is to round the edges so that the arc has good access to the sidewalls. In this example, it's also about the depth of grinding. So as you grind deeper, you also want to make sure that you V this out. So there are many key factors to implementing and operating a successful welding operation. Best practices bring the best results. While there are many facets to implementing and opening a successful best practice, so it's a method or technique that has been generally accepted as superior. So best practice is developed from experience. Companies should invest in training, implement effective preventative maintenance programs, and best practice should become the standard way of doing things. So if anybody has any welcome back everybody. So let's have a look at weld quality control. So how do we control quality? One method is to use visual inspection and visual scanning. Visual examination has the greatest benefits for the lowest cost. Visual examination can minimize the need for more advanced and expensive testing, providing visual scanning occurs before and during welding, and visual inspection is done after welding. Everyone involved in making the weld must participate. So we'll have a look at some ideas on how to include visual scanning into a visual examination plan during all phases of fabrication. Let's start with some of the welding fundamentals. There are many different types of joint designs. The main joint types used for welding are a fillet joint, which may use square edge plates or a bevel plate depending on the amount of penetration required. A square edge joint, which can have no gap, known as a tight butt or an open gap. A bevel groove, where only one plate has a bevel and the other plate has a square edge. This is also known as a single bevel groove. A V groove, where both plates are beveled. A J groove, which is commonly prepared by machining. And a U groove, which can be prepared by machining or gouging. When the material is thicker, it becomes more cost effective to use a double-sided groove joint. The joint preparations shown here are a double bevel, also known as a K-joint, a double V, a double J, and also a double U. The recommended changeover thickness to start using a double-sided joint is 20 to 25 millimeters. As an example, a double V groove joint in 25 millimeter thick material will require half the weld metal of a 25 millimeter thick single V groove joint. So let's look at welding terminology that we would use for visual inspection. These definitions are from the American Welding Society, AWS A3.0, which is the standard for welding terms and definitions. So the weld toe is where the weld face meets the base metal. The weld face, also known as face, is the exposed surface of the weld, the part that we see on the side from which the welding was done. Reinforcement, also known as weld reinforcement, which should be referred to as face reinforcement or root reinforcement, and is the amount of weld metal in excess of the quantity required to fill a weld groove. The groove face is any surface in a weld groove before welding, also known as bevel face, which is the prepared surface of a bevel. The root face is also known as a land and is the portion of the groove face within the joint root. The root opening, also known as gap or root gap, and the root reinforcement is the weld reinforcement opposite the side from which welding was done, and is often referred to as penetration or melt through. Fabrication standards usually specify that the weld toes should blend smoothly, and many fabrication codes specify a maximum weld reinforcement height. This is very important as the reinforcement height will affect the weld toe angles. The higher the toe blend angle, the greater the amount of stress concentration. Ideally, the toe blend angle should be between 20 to 30 degrees. Certification tests for welders can also state toe blend angles. Australian Standard AS 1796, Certification of Welders and Welding Supervisors, states the angle should not be less than 135 degrees. Care must be taken to note how the weld toe angle is measured. For fillet welds, there are also specific terms to describe the weld features. Fillet weld leg is the distance from the joint root to the toe of the fillet weld. Fillet weld size is typically specified based on the leg length. In unequal leg fillets, the size of both legs, vertical and horizontal, will be specified. Design throat thickness, or theoretical throat, is the distance from the beginning of the joint root perpendicular to the hypotenuse of the largest right angle triangle that can be drawn within the cross section of a fillet weld, based on a root opening of 0. The design throat thickness for all fillet welds at the correct design strength is 70% of the leg length. This is different to the actual throat, which is the shortest distance between the weld root and the face of a fillet. This picture shows the difference between the design throat thickness and the actual throat thickness. There are 3 different types of fillet welds. There's a mitre fillet, has no reinforcement and has the correct design throat thickness, which is 70% of the leg length. A convex fillet has an increased throat thickness due to the reinforcement. So this is the convex fillet. And the concave fillet, it's often preferred for joints subject to fatigue loading, but the throat thickness will be undersized for the leg length. For a concave fillet weld to meet the design throat thickness, longer leg lengths and a bigger fillet weld size is required. This is the AWS ASME, so that's American Welding Society and American Society of Mechanical Engineers, and the ISO Welding Position terminology for fillet welds. AWS uses 1, 2, 3, 4, and 5. So these being the positions for flat position or downhand. The number 2 is horizontal, 3 is vertical, but the AWS system does not define if the weld is done vertical up or vertical down. And number 4 is overhead. The number 5, position 5 and position 6 are specific for pipe welding, where the pipe axis is horizontal and the pipe is fixed in position and the weld is done vertically. For AWS, the vertical method, whether it's vertical up or vertical down, needs to be specified. ISO uses a similar system which is based on a square and specifies if the welds are done vertically up or vertically down. So in the ISO system, PA is the flat position, PB is horizontal, PB is horizontal vertical, so that's fillet, PC is horizontal, PD is an overhead corner or fillet weld, PE is overhead, PF is vertical up, and PG is vertical down. There is another terminology for PH, which is specific for pipe with a fixed in position, which is welded vertical up. PJ is a pipe joint fixed in position with the pipe axis horizontal, where the welding is done vertical down. AWS has a 6GU is a joint where the pipe axis is at 45 degrees, fixed in position, so that's not rotated, and welded vertical up. So G means groove, so this is a groove joint. Position 6 is where the pipe axis is at 45 degrees. The U indicates the welding is done in the upward direction. 6GD is a 6G joint welded vertical down. There's also in the AWS system a 6GR, which is a 6G joint with a restriction ring. And the restriction ring is to simulate a TKY joint, typical of offshore structures. And then in the ISO terms, they use HL045. So the H is for the vertical up, and L means the level, which in this case 045 means 45 degrees. This number can also be changed. If it was 060, then it would be the pipe axis is at 60 degrees. And then a JL045, usually called JLO45, that's vertical down welding with the pipe axis at 45 degrees, indicated by the 045. So it's good to use the same terminology when describing a pipe joint and also the position of welding, because the AWS ISO terms are standardized globally. So when we use standardized terminology, we all understand what we're talking about. The other option, of course, is if it's a unique joint, then that would require a drawing or a picture. So when we look at welding, we need to ensure that the process is right for the application. The joint configuration must be suitable for the welding process and also the welding position. To assure uniform results, the procedures must be explained in detail, set accurately on the equipment, and followed correctly during welding. By using full-scale mock-ups or simulated joints to prove the process and procedures give the required quality, and qualified people must be assigned to do the jobs. So that's the 5 P's of welding: process selection, preparation, procedures, pre-testing, and the personnel. So when we look at process selection, with various automatic and semi-automatic processes available, process selection can be a challenging decision. Always remember that there are many resources available to assist with selecting a welding process. This could be the specific fabrication codes or maybe the internet. The process selection will also be determined by the requirements of the joint design, and the welding position. It is important to consider under what conditions will the joint be welded. Will the joint be welded in the workshop using manipulating equipment, or will the joint be welded on site? What are the site conditions? What equipment and personnel are available? Which processes are already available for use? The pictures are examples of joint design showing how the design will affect the welding. In this first picture, welding the first vertical plate using a stick electrode, that's SMAW process, is very easy. So we weld this plate, very easy to do. The stick electrode has easy access. But when the welding comes to the second vertical plate, then trying to weld that plate, this one, the second plate, you can see that the electrode access is restricted because of the first plate. So that makes the joint difficult to weld, and it may require a different process or a redesign. In this example, where a C channel is made wider by putting in a winding plate, the joint can be easily welded if the plate is put under the section rather than on top of the section. So that's a simple matter of positioning of the material. So this is a chart of items to be considered when selecting a welding process. The factors to be considered are the design limitations. The material selection will determine the weldability, and if there are any special precautions required. Some of these special precautions could include color match if welding weathering steels that are often used for steel buildings where the steel is exposed and not painted, or bridges because the steel does not need to be painted. It could be quenched and tempered or TMCP steels where thermal processing is used to increase material strength. With these materials, preheat and inner pass temperatures, as well as weld metal hydrogen control, are very important. Stainless steels or aluminium, where cross-contamination from carbon steel products needs to be avoided and requires dedicated work areas or different buildings. The product design will affect the types of welding processes used and requires a knowledge of good fabrication practice. An example of weld process capability is knowledge of how to fully weld internal stiffeners in box columns, which requires electrogas or electroslag welding to complete the final joints. Specifications and QC standards are used to ensure the design has the appropriate fitness for purpose requirements, which will include specific mechanical property requirements, post-weld heat treatment assembly, and handling instructions. Then there is the need to consider the fabrication limitations. The shop facilities where the fabricator has suitable welding equipment or can obtain the correct equipment to complete the project, if the fabrication shop has suitably trained people or is willing to invest in training. The auxiliary equipment, fixtures, positioners, turning rolls, loadout facilities, handling are appropriate for the project and to ensure the safety of everyone working on the project. The most important aspect of process selection is usually the management philosophy. When the management of the company can see the benefits to upgrade knowledge or invest in new equipment and training, it makes the transition to introduce new ideas and welding processes a united team effort where everyone will learn and benefit. After the design and fabrication limits have been identified, it is then possible to select a welding process that will provide the highest cost-effective productivity, which will then allow the welding procedures to be developed. Let's look at preparation. Joint preparations are standardized and specified by applicable codes. The decision of the joint preparation is often made by the designer rather than the fabricator. The fabricator is usually allowed to select which process and procedures will be used to make the weld. Acceptable butt joint preparations are a compromise between the included angle of bevel and the root gap size. A larger included angle will allow the use of a smaller root gap, and a smaller included angle will require a larger root gap for proper electrode access. This picture shows the difference between two different bevel angles that have the same root gap. So it's very important to follow specifications and ensure correct fit up and correct joint design for the process. The electrode on the left can access the root of the joint easily, but the electrode on the right has restricted access. To give the electrode the correct root access, the root gap needs to be increased or a different process used. To achieve the required weld quality, the joint must be correctly prepared to meet the specifications. There should be a visual inspection plan in place to ensure the materials are prepared correctly. So for procedures, reliable welding procedures are developed through first-hand experience and must be recorded correctly to ensure any trial and error when developing the procedure provides useful data for making adjustments. They should be completely detailed and qualified before production begins. The welding procedure specification should include special precautions required, such as handling of TMCP or quenched and tempered steels, any precautions for the method of plate preparation, preheat temperatures, interpass temperatures, and requirements for post-weld heat treatment or stress relief. Pre-testing of production-sized or simulated production specimens confirms the process and procedures are suitable for the application and allows the test specimens to be also used as a final check on the qualifications of the operator. The closer the test conditions replicate the service conditions, the more accurate the results. The proper use of process procedure qualification and satisfactory test results will make the final inspection easier. Welding operators and everyone involved in the fabrication process should be trained and assigned the responsibility to conduct visual scanning on all components and empowered to feel confident to provide feedback on items that require additional inspection. So how to conduct visual inspection? Visual scanning and visual inspection is generally the same for all applications. The quality of the welding can be defined by a specific welding code or maybe a client specification. The welding quality could be general purpose, special purpose, fatigue purpose. Visual inspection can be used to prevent welding problems from happening, and there are different guides for visual inspection. Some examples are AWS B1.11 is the guide for visual inspection of welds giving general guidelines. AWS D1.1 is the structural steel welding code, which includes different sections relating to visual inspection for procedure qualification and welding operator qualification. Visual inspection can help to save time and resources by correcting errors before they become defects that require repair. To conduct visual inspection, it requires practice to develop the necessary skills and experience. So the role of visual inspection. is to determine if the required visual quality has been met before using other forms of non-destructive testing, such as radiographic testing or ultrasonic testing. It is best to correct any visual defects before conducting additional testing. By making the welding more precise by following a proper process procedure method, the final inspection can become more of a quality control function. The idea should be to make the welding so precise in giving the required quality that all subsequent inspection is for the detection of the unexpected and unexplained, rather than defects that can be explained or could have been found during production. No amount of after-the-job inspection will improve the weld. After the weld inspection defines that is acceptable and what must be reworked, repaired, or rejected. The visual scanning, as the job progresses, is different to visual inspection. Visual scanning can be done quickly as parts are assembled and will detect errors in technique and defects while correction is still possible. By using visual scanning, it can help to prevent minor defects from becoming major defects that may lead to the parts being rejected. Visual scanning will be the main method of checking quality, and it is one method that can be applied routinely while the job is in progress. The object of visual scanning is not only to look for flaws, but also to find clues about what may need attention in the entire fabrication process. Presence of excessive porosity and slag inclusions may be an indication that the welding current is not adequate. The welding machine could show the correct meter readings, but there can also be variations caused by coiled welding cables or poor connections. Subsequent tests will also give clues to faults in equipment which require maintenance or in the welding procedure. The information acquired through visual examination, whether that is by scanning or inspection, allows corrections to be made before conducting more extensive testing. Visual examination includes both visual scanning and visual inspection. Visual scanning occurs during the fabrication process. Visual inspection occurs after the welding has been completed. Visual scanning is done quickly without tools. Visual inspection requires good eyesight and simple tools: a rule, weld gauge, magnifying glass, a straight edge, and a square. Everyone connected with the job, including the formal inspector, participates in visual examinations. So visual inspection before. Visual inspection should be conducted when the material is received to ensure the material meets the specifications and all documents and material marking is correct and the material is free from defects. Visual inspection should also be done before the materials are prepared to ensure the correct grade of material and thickness is being used. Excessive foreign matter should be removed before preparation. Now, this is an example of some bubble wrap plastic that was stuck by rust onto the weld bevel. Before assembling prepared parts, a quick visual scan should be conducted to ensure that all drafts from oxy-fuel cuts, uneven surfaces from shear cuts, or surface gouging from poorly maintained cutting equipment is removed or recut. Take note that some structural standards may require thermal cut surfaces on quenched and tempered steels and other specific grades to be ground back by 2 to 3 millimeters to remove the hardened surface produced by thermal cutting. So as we look at these cuts, this one has a lot of gouges in the surface. So without a lot of grinding to remove all of these gouges, that's going to be very difficult to weld. It can be done, but it may include a lot of slag inclusions. This one has been ground back nicely. This is a much better prepared surface. This is a preliminary scan done with a quick look, but can have a significant factor in weld quality. So we're looking at the alignment and fit up of parts. Good preparation makes welding easier and the quality better. So here you can see there's a very big change in the root gap here, which will make it more difficult for the welder to make a good root pass, which it will require additional back gouging or additional rework from the second side to make sure that this has good penetration. This one is a very nice even gap that's going to be very easy to fill. Most probably won't need any rework from the second side. And there is some slight gouging in the bevel face here, but it's not too deep, so that won't be a problem. You can see the differences in the preparation of the parts. So a visual scan before welding will show if parts are aligned and the fit up is correct. In the top picture, poor fit up may cause melt through, which will require a repair or possibly the part to be rejected. On groove joints, it is important to clean the correct surfaces to ensure defect-free welds. So with filler welds, people will quite often clean the top of the plate, but they will forget to clean the underside. So it's very important with a square type fillet weld that the underside of the plate here is also cleaned to remove any contamination, because as you start the weld, any contaminants on this underside will escape through the weld and can create porosity holes. It's the same in this example. Just cleaning the top is not good enough. You need to clean the top surface as well as the two surfaces that butt together. In this example, there's a lot of forming oil that's on this plate that hasn't been cleaned off, and that's a potential porosity hazard. So things to consider is the joint preparation, the inspection, the pre-weld setup, correct joint alignment, the metal surface condition and cleanliness, the metal temperatures prior to welding, so if pre and post heating practices need to be applied, the shielding gas type and also protection from any drafts if you're in an open workshop, preheat verification, temperature and heating method, the presence and location of heat treatment monitoring devices. So all of these need to be considered and looked at. These pictures show items that will affect the welding procedure. This picture shows a large welding cable connected correctly to a bolt, but then bolted on a steel plate, but the welding current is going to go through a small tack weld that becomes hot. This picture shows a work clamp with a worn welding cable. Anytime a welding circuit has hot welding cables or hot connections, this indicates resistance in the welding circuit, which will affect the welding voltage. This can cause stick electrodes to be hard to strike, or in MIG welding, if there is a loss of voltage, this could cause excessive spatter or possibly the wrong transfer mode. This picture shows a welding cable wrapped around a steel beam. So anytime welding cables are coiled, they create an electromagnet, which causes loss of welding current. Depending on the length of the welding cable and what it is coiled around, it is possible to lose 80 amps when welding. The ammeter on the machine will have the correct reading, but the welder will be trying to weld with much lower amps that can cause slag inclusions with stick electrodes. The points to remember are hot connections or welding cables will affect voltage. Coiled welding cables can affect the welding amps. both of which can cause welding procedure changes and possible defects. So visual scanning during the welding process, that's the most productive. It's good practice to inspect every weld pass, as it can reveal cracks, porosity, slag inclusions, or a poor pass placement. For a root pass, you can visually check the root pass to see if there's inadequate penetration. You can also check if there's overwelding or underwelding. In these pictures are typical for submerged arc welding, where the electrode placement for the next pass is important to ensure correct access to the joint, but also correct bead placement, and it's typically 1 wire diameter away from the sidewall. So visual inspection after welding should always be done before using other NDT, non-destructive testing methods. Bad welds should be corrected before other non-destructive testing inspection is done. Visual inspections are a type of non-destructive weld test, and as an example, in the Australian Standard AS 1554 Part 1, the suggested extent of, that's the structural steel standard for Australia, the suggested extent of non-destructive examination for structural welds is 100% visual scanning. It's 10 to 50% visual examination, followed by 0 to 10% magnetic particle or dipenetrant, that's only for repairs, or 0 to 10% RT radiography or ultrasonic testing for materials thicker than 20 millimeters. So different standards from different countries, different class specifications will have different requirements, but typically visual scanning should always be 100%, and everybody can do that as they're going through the fabrication process. So visual inspection after welding, the most common post-weld visual inspections include examining for these types of discontinuities: undersized welds, undercutting, weld overlap, surface cracking, surface porosity, underfill, incomplete root penetration, excessive root penetration, burn through, excessive reinforcement or correct bead placement, and proper placement of the weld. These are some inspection tools. So there's a multi-purpose weld gauge, there's special gauges for checking misalignment or high-low. There's also different types of fillet weld gauges. Knowing how to use fillet gauges correctly is also important, and you should practice using your visual inspection tools. So for a fillet gauge, the way this works is, on the bottom of this cutout on the fillet gauge, this aligns with the toe of the weld, and then this line here, when you project that downwards, that aligns with the other toe of the weld. And then for checking the throat thickness, the way that this works, you can see these two lines here. So this flat surface is here, so that should touch the face of the weld. And then when you project those two lines, they should line up with the toes of the weld. And that's the correct way of using a fillet gauge. And knowing how to use a fillet gauge correctly is actually quite a big topic. This is the Inspection Trends magazine from the American Welding Society, and this has an article in it about using fillet weld gauges, and these are some screen grabs from that article. So for weld appearance, the beginning of the weld, end of the weld, so the things that you're looking for is you're looking for straight edges. So we want to have straight edges. You want to be seeing a consistent type of ripple. There's no extra arc strikes outside of the weld groove, they're defects. Want to make sure that the end crater is correctly filled and there's a nice smooth surface. This weld here obviously does not look so nice. The edges here are not straight. Some parts here have not filled the bevel correctly. There's a few lumpy bits in there. So weld appearance, very important visually to have a nice appearance. So tack welds should be aligned with each other and spaced to hold consistent root gaps. If you're doing a root weld, you should have full and consistent penetration. The end crater is filled to the height of the weld bead. There's no extra arc strikes on the metal surface. So the ideal weld is consistent. The weldment has a consistent width, height, shape and appearance from the beginning to the end. It's smooth in the face with dense ripples. The appearance will indicate a consistent travel speed, an excellent rod and puddle management. The weld is free from slag, porosity or spatter. The operator spent adequate time to remove all contaminants from the base metal before welding. The operator chose the correct process and consumables to perform the weld, and the operator selected an appropriate travel speed, arc length when doing the weld. So when you have a good appearance, it also shows the workmanship of the welder. So weld appearance should be consistent and even. There's no undercutting. So undercutting will show that the correct welding current, travel speed and electrode angle were used. There's no overlapping or overfill, so the operator used the correct techniques. So discontinuities, they're also known as imperfections. So being able to distinguish between a sound weld and an unsound weld begins with visual examination. Visual scanning and visual inspection at a basic level only require good eyesight. So discontinuities are also known as imperfections and are an interruption of the typical structure of a material. Discontinuities are not necessarily defects. However, if the discontinuity is too large or repeats too often within the weld, the discontinuity can become a defect. Defects will compromise a weld's overall strength. So this is just a picture. So it's showing the stress concentration. So if you have a sound weld with no imperfections, then the stress concentration will travel all the way through the weld. But if you have a imperfection, then that creates stress concentration around the imperfection. So arc strikes, there's some pictures of arc strikes. So they're random areas of fused metal where the electrode, it could be the electrode holder or the return clamp accidentally touched the workpiece and produced a short duration arc. It can happen when there's poor access to the work. It could also happen if there's missing insulation on the electrode holder or the welding gun. It can happen if there's failure to provide an insulated resting place for the welder to put down the electrode holder or the welding gun when it's not being used. Or a loose work cable clamp can also arc and create an arc strike. So arc strikes will also create a hardened area in the base material. Usually they're defects, not acceptable. Burn through. This is an example, a picture of a burn through. So it's when you have the welding arc just melts completely through the base metal. It's generally caused by having too much heat or a poor welding technique. Could also be the result of having a root face that is too small or a root gap that is too large, and also a slow travel speed. This is an example of root concavity, so we can see that here. So this is our base material, and then the root pass here, we can see that's a concave shape. So instead of having this part where you've got nice penetration. This one, it's sucked back. So it's a shallow groove which may occur in the root of a butt weld. So for stick electrode welding, typically caused by an incorrect electrode choice or lack of welder skill. If this is a TIG root pass, it could be because your purging gas had too much pressure. So here we can also see some root defects. So this side here, haven't fused to the bottom edge at all. This one here, that's a lack of root penetration. This part here is excessive. This part here, it's nice, it's fused both edges. There is some good penetration there. So there's an example of root defects. This is an example of a crater pipe. So this is a small shrinkage cavity. It's like a porosity hole. But this one generally always caused by a lack of welder skill, and it's caused by stopping in the middle of an open root joint. So the correct method of stopping when welding an open root joint is to make sure that you stop on the side wall. If you stop on the side wall, it doesn't create a crater pipe. So that one is a little bit of retraining required. In this example, improper or excessive reinforcement. So here we can see that there is an excessive amount of reinforcement. So it's excess weld metal that causes convexity in fillet and butt welds. So improper or excessive reinforcement indicates too much or too little filler metal. Possible causes, incorrect travel speed, shallow edge preparation, or weld pass placement, which would require retraining and additional practice to develop experience. How you stack the weld passes in a multiple pass weld will affect your reinforcement. So inter-run imperfections. So visual scanning after every weld pass would have shown this imperfection, most likely a slag inclusion, so we have one here, which could have been ground out before welding the next pass, which could have saved doing a repair by gouging and additional testing. So if the visual inspection had been done, this could have been found, cleaned, removed, but after the cap pass has been welded, the only way you would find that slag inclusion now is by UT or RT, so ultrasonic or radiographic testing, and now this becomes a documented repair because you have to follow the repair procedure to remove this slag inclusion. So at the bottom of the weld here, there also appears to be some lack of fusion in here, which could have been re-welded before completing the joint, where the imperfection now also becomes a repair. So that's the importance of doing a quick visual scan between weld passes. And so as we look at slag inclusion, so it's pockets of slag in the weld, so there's some here. Can be caused by low heat input, improper techniques or motion, so that's either a whipping or a weave technique. As we look at slag inclusions, so it's slag trapped during welding, could be caused by heavy mill scale or rust. Could also be caused by slag flooding ahead of the arc, so that's because your travel speed is too slow. The slag from the welding process will go in front of the arc and then you weld over it. It could be unfused flux due to a damaged electrode coating. This is typical of stick electrodes. Really low hydrogen electrodes, if they've been overbaked, then the coating becomes extremely dry and brittle. The coating can break off and go into the weld. And this is a very important note. You cannot weld over submerged arc slag. So if your welders are using the submerged arc process, they can't get the slag out, they have to grind it out. There's no choice. Get in there with a grinder, grind out all the slag. If you try to weld over the slag, it will be a slag inclusion. Yeah, that's the nice thing about submerged arc. So for slag inclusions, there's also bead placement makes a big difference. So in this picture, this one has easy slag removal. In something like this, it's possible that you can create some undercut on the sidewall. If you create undercut on the sidewall, as shown here, that locks the slag in. It's going to be very difficult to impossible to take out. So when you have split passes per layer, in this example, the slag is much easier to take out. When you have full layer single passes, it's quite possible to undercut the edges and that will lock in the slag. And then there's also bead placement. So this one, very important to have the correct bead placement to ensure that the electrode can reach to the bottom of the joint. So in this example, what happens here is, because of this weld pass is slightly out of position, the electrode cannot touch the bottom of the joint. And this is with all processes. So it could be submerged arc, it could be a stick electrode. If the electrode cannot reach all the way to the bottom of the joint, you need to grind this part away so that the electrode can touch the bottom of the joint. So the electrode must be able to touch the bottom. If it doesn't, you'll end up with some trapped slag in there. And that's usually a lack of experience. That's what affects poor bead placement. So that's where you need to weld a lot more, develop more experience. So when you have correct bead placement, the electrode, seen here, can touch to the bottom of the joint. So when that happens, you'll have good arcing into the previous weld pass and also the sidewall, and you won't have any slag inclusion. In this case, what will happen is the arc will bridge to the sides and you'll end up with this slag inclusion or a hole in the weld. So that's very important. So slag inclusions, it's incomplete slag removal, trapped slag. So the important takeaways: you cannot weld over submerged arc slag. Poor bead placement, you need to ensure that the electrode can reach the bottom of the joint. You also need to ensure that you have the correct bevel angle and root gap for the process that's being used. So here's some other examples. This is incomplete fusion or a lack of fusion. So a lack of fusion between the weld metal and parent metal at one side of the weld. And you can see that along here. There's this straight line there. So that can happen with low heat input. Could also happen with molten metal flowing ahead of the arc, so that's slow travel speed. So the metal is flowing on top of the weld, not fusing into it. And oxide or scale on the weld preparation. A lot of times the oxides have a much higher melting temperature than the base material. So if you have oxide on the bevel face, then it prevents the fusion. This is an example of incomplete penetration. So here we can see this is a very cold looking weld, and you can still see the edges of the root face. So it's when the weld bead does not completely go through the base metal, or where the toes of the weld bead do not melt to the base in the base metal. So that's poor fusion. Right. Oh, there's a question here and what is the maximum thickness a plate can be welded for single bevel weld? It doesn't matter. You just put in a lot more weld passes. So it really depends on your application and what method you have for preparation. But a single bevel weld, it could be an unlimited thickness. You just put in more weld passes. Great, thank you. So this is an example of excessive root reinforcement. So here we can see this is really excessive. And there's a big blob there as well. So it's when the weld energy, it's too high. so it's root reinforcement beyond the specific limit. So incorrect weld preparation, maybe the root gap was too big, maybe the root face was too thin, there was a lack of backing, it could be the wrong electrode or the wrong welding position, it could also be a lack of welder skill. Another example that can be found through visual scanning is misalignment. So misalignment is also known as high-low. So the pieces of metal, they're not aligned on the same plane, so the metals were not set properly prior to welding. So it's an inaccuracy in assembly. It could be excessive outer flatness in hot roll plates, or it could be the material tolerance with pipes. All pipes will have a acceptable tolerance, but most codes will have a limit on the acceptable amount of out of round or high-low. So if you receive material that's out of specification to the standard, then it should be rejected and returned to the supplier. And there have been cases where customers do buy out of spec pipe because it's a much lower cost, but then they have a lot of challenges with doing the welding because the fit up is very poor. So the money you save on material costs, you lose in the additional time needed by the welder to try and fill big gaps in high-low. Overlap. This is overlap here. So you can see the weld metal has flowed and it's overlapping the base material. So it's an imperfection at the toe of the weld caused by weld metal flowing on the surface of the parent material. So usually a result of poor welding technique. A lot of energy, so that's high currents or low travel speed that allow the weld metal to flow over the surface. Incorrect position of the weld or the electrode where the weld metal is too fluid. Porosity. This one's porosity, so you can see these. Porosity is usually a line down the center of the weld because that's the highest point. So as the weld metal is cooling, the gas bubble just travels up to the highest point. So the gas pores that actually break the surface of the weld. It could be from damp or contaminated surface or electrodes. It can be from a loss of shielding gas due to having a long contact tip to work distance or high winds with the GMAW process. Okay, thank you, Ting. Ting's answered the question. This is an example of porosity that's in a submerged arc weld that's being removed by gouging. So when you do have porosity in a weld, in this case with submerged arc, the porosity is usually caused by contamination in the flux. Doing a repair by gouging, it can become a very time-consuming repair as the porosity holes can be very big. Excessive spatter. So spatter is small drops of weld metal projected out of the weld, and these confuse to the parent metal. It can also happen with arc blow. So this is if you're welding into a corner joint where the magnetic fields interact with the arc. With the GMAW or MIG welding process, it can be a case of incorrect settings, or maybe you've got some coiled cables or a hot connection that's reducing your voltage. Quite often occurs stick electrodes with damp electrodes. Yeah, you can see there's a lot of porosity on this plate, but this was a result of the surface coating. So you can see there's some oil on the surface here, and that creates spatter. Undercut. So this, in a fillet weld, it will usually occur on the top edge. So what will happen is when you're trying to make a fillet weld that's too big, or you're traveling too slow, or you have an excessive amount of weld metal, what will happen is the weld metal will undercut on the top edge as it flows down. So typically you will end up with overlap or overroll on the bottom plate and some undercut on the top plate. So that's typically this one. That's most common cause is trying to make a fillet weld in the 2F or PB position that's bigger than 9 millimeters, and that's a limitation of gravity. So with any welding process, the largest weld that you can make in this horizontal vertical 2F position is typically 9 millimeters. If you try to go bigger than that in one pass, so that's a one pass weld, then you'll end up with this undercutting on the top edge and this overall on the bottom. Another defect to see, another discontinuity is undercut. So this is on the cap. So for undercut on a cap, you need to refer to your specific code to measure the depth and the length to see if it complies with the code requirements. Underfill, this one we can see here, the weld metal has not reached to the level of the base material. So this one, it just needs another 1 or 2 passes of weld metal. So that could be a lack of experience, it could be poor bead stacking. Weld profile, this one is showing a poor stop-start. So this one is where the crater wasn't properly filled when the weld was stopped, and the start didn't fill the hole that was left in the crater. So this one here also shows a poor stop-start there. You can also see that there's a bit of a hole in the weld there, and we don't have even edges. So this, the top side is not bad, it's quite straight, but on the bottom side the weld comes out here and then goes back in again. So the weld profile, this one, this position here, we can see the weld is in the correct position, it looks good. But then as we come to this part, the weld has become narrower, more peaky, and it's also traveled up the sidewall a little bit. So this could be a result of arc flow, which is magnetic fields. It could be wire wander from a worn tip, but this must be repaired by grinding or gouging before welding the next pass. Because what will happen is, when you weld the next pass over this, it will actually amplify, or it makes the poor appearance of the previous pass more obvious. So sometimes very difficult to fix by just trying to weld over it. It's best to grind this out, gouge it out, get the correct bead shape back again, the correct profile, and then weld over it. This one, the gouging profile, so poor gouging or grinding profile. This can restrict access to the joint that causes slag inclusions, and it can mean that extra welding will be required because you might have to go back and do a second repair. So this is a gouging profile. So this is the correct weld profile. The weld is very nicely put in the correct position. It's got a great uniform appearance. In this picture, a repair was done. This area here, the bevel face was gouged back too far. So now it's going to need extra welding to fill that up. It could also cause a slag inclusion, so that creates extra welding time. Here are some defects. Defects are an unacceptable amount of discontinuities, so that's imperfections or flaws. It can also be an unacceptable weld, and the weld is rejected. So here's some examples of desirable fillet welds. So this one being concave, this one slightly convex but has more of a mitre shape. And then this one, we're seeing excessive convexity, so that could have some undercut on the top edge here. It's almost getting into an overall on the bottom. This one, the leg length is insufficient, and this is an unacceptable fillet weld. So here, incomplete fusion. So that's some examples. And then this one is actually a defect of the material. So this is what they call a lamination. So this usually happens during the hot rolling process. As the materials are rolled, you'll get a buildup of impurities. So you could have a segregation line. If you have a complete lamination, then you can see how this is opened. So the parent material should be inspected for any visible defects, and sometimes that's why they specify the through strength testing or the Z testing of materials to make sure there's no laminations. Okay, question there about how to know the incomplete fusion for a fillet weld. Well, you have to use ultrasonic testing, radiographic testing. That's the only way you could do it. If you look at the face of the weld, you won't see incomplete fusion because it's a fillet. But fillet welds usually quite difficult to get incomplete fusion unless you're traveling extremely slow, trying to put in a big weld and the weld metal flows in front of the arc. But you would need to check for incomplete fusion using radiographic testing or ultrasonic. So a visual inspection plan and the responsibilities, it should be with the welding supervisor or the foreman or any special employees. There's also a client responsibility to check everything to ensure that the workmen are following the specifications. For inspection, you need to have qualified trained people, and the pre-weld inspections, the welding operation inspection, so all of the inspection plan should be described and developed into a complete plan, an inspection test plan. So as part of that plan, you would also need to determine how the inspections will be completed and who will be the people doing the inspections. The primary purpose should be to consider problems before they occur and become problems. The welding inspection is divided into 3 areas typically: the pre-weld inspection, and then inspection during the welding process, and of course the inspection after welding. And everything needs to be documented when it's an inspection process. Visual scanning, a little different. You're just having a quick look to make sure everything's okay. So this is an example of a basic plan. So we just divide that out into sections. So in the pre-weld inspection, what would you look for? You would check that the weld metal is being properly cleaned, that the weld joint preparation is accurate, that you're using the correct electrode, and the welding variables in the WPS or shop procedure. So you make sure that you're using the correct polarity, you have the correct amps. I would also include checking for things like coiled cables, loose connections. And then during the welding operation, for the inspection and the scanning, you wire brush cleaning between the welds. So that could be a powered wire brush. The slag is properly removed. You check that the weld is in the correct place. If the electrode can't touch the bottom of the joint, then you make sure that you grind out the previous weld pass so you have good access, so you don't get a slag inclusion. You would check the parameters, the amps, the volts, the travel speed, and you would inspect each weld pass. And then for a post-weld inspection, obvious things you'd look for: undercut, surface cracking, porosity, and a correct weld profile, that the weld looks good. So this is an example of a weld inspection sheet. So this has the requirements, the design throat thicknesses. It also specifies the job description. It has the standard it refers to. So then you can record the information that's been inspected. So this is another example. So this one, we have the action plan, the person that's responsible for it, and how often the procedure is conducted. is another example. This one was from a pipe mill, but so that's why we've got API 5L, because that's a pipe standard, but it's looking for the amount of high-low. So you have different diameters, different thicknesses, so it's the amount of allowable high-low for the thickness, any dents, the weld bead height. So this is the requirements that would be looking for during the visual inspection. So in summary, a good pre-weld inspection plan can help prevent welding problems before they start by detecting problems that can cause weld defects and discontinuities. Weld operations inspections help to ensure that the welding processes are being completed correctly. And post-weld inspections can be very effective and a cost-effective method for improving weld quality and saving time and resources. And it's always have a weld inspection plan. So if there's any questions about this, we did have some questions during the presentation. That was really great, so thank you for asking questions. If there's no questions, we can go for a 5-minute break, and then we'll be back to have a look at a consumable certificate of conformance. Welcome back, everybody. Let's have a look at the consumable certificate of conformance. So most of the time when we ask a manufacturer of welding consumables for a certificate of conformance, it is simply to have a copy on file. But sometimes there is a need to actually read and check the conformance certificate to make sure the filler metal meets the mechanical and physical requirements for the specific application. This is a typical certificate of conformance for an E7018 SMAW stick electrode that was downloaded from the Lincoln Electric website. Certificates of conformance contain a lot of information. This presentation will explain the information found in a certificate of conformance and how the process for classification is done. So for this presentation, the case study electrode is an E7018-H4R. So to explain the classification, E is for electrode, 70 is the minimum tensile strength of the weld metal in thousands of pounds per square inch. So 70 means 70,000 psi minimum tensile strength for the weld metal, and sometimes that's abbreviated to KSI, which is thousands of psi. 18 is the welding position, the type of flux coating and polarity. So the number 1 means the electrode can be used in all positions, downhand, vertical and overhead, and the 18, so that's both numbers together, means the electrode flux coating is a potassium-based low hydrogen type with added iron powder for increased deposition rates. The polarity recommended for an E7018 is alternating current or DC electrode positive. The H4, this is an optional designator for the diffusible hydrogen content of the weld metal, which for this electrode is 4 milliliters of hydrogen for every 100 grams of weld metal. The R, this is also optional and indicates the moisture resistance of the electrode coating, which means how easily the flux coating on the electrode absorbs moisture. The specification for this electrode is AWS, so that's the American Welding Society. It's A5.1, which is the specification for carbon steel electrodes for shielded metal arc welding. So a certificate of conformance conforms that the consumable conforms to the chemical and mechanical requirements determined by the specification for the specific filler metal. In our example, the electrode is being classified using the American Welding Society system. Manufacturers are not required to test every single batch of product produced. Depending on the filler metal, the classification test can be done every 1 to 3 years. These certificates are known as typical certificates and confirms that the product the customer receives is made with the same manufacturing process as the product that was tested for the classification test. A certificate of conformance with typical values complies with the European EN 10204 as a type 2.2. So I'd like to highlight that with a typical or 2.2 type certificate of conformance, the actual product supplied is not tested. So for an E7018 electrode, the certificate of conformance has 5 main areas. The operating settings, which has the amps, the number of passes, layers, and preheat inner pass temperature information. The mechanical property information, there's the chemical composition or the chemistry analysis, the fusible hydrogen information, and the coating moisture. Other items in the specification that must be met for classification include diameter, the length, the exposed core, so that's how much of the electrode is bared at the end to be put into the electrode holder, the electrode identification marking, so that's the stamp that's on the end of the electrode, the packaging, and also the labeling on packages, which must include the supplier's name, the trade name, the size and net weight, lot number, control number, and heat numbers. So there's a lot of requirements that need to be met for an electrode to be classified to a specification. So this is the joint design for an AWS test plate. The included angle is 20 degrees plus 5 degrees minus 0. The material grade, thickness, joint type, the grade of backing material, as well as the backing material dimensions, the root gap, preset angles are all specified in the specification. As an example, for a 4mm 7018 electrode, the test plate material is 20mm thick. The root opening is 16mm. There must be 2 layers per pass and between 7 to 9 layers for a total of 14 to 18 weld passes. The preheat temperature is 105 degrees C minimum, and the inner pass temperature between 105 to 175 degrees C. So welding test plates is a lot of work. If a company manufactures 200 different types of consumables, so that's SMAW, GMAW, FCAW, and SAW, so stick, MIG, flux cord, and submerged arc products, to test one diameter of each product will require 200 test plates, which is about 4 test plates per week. So multiple test plates are welded at the same time to make it easier to maintain interpass temperatures. While one test plate is cooling, another test plate is being welded. This is an example of a test plate welder with stick electrode process. And this wire you see here is a thermocouple for measuring the plate temperature. So these pictures show the location of the test specimens in the AWS test plate. The test specimens are a tensile test, which determines this is the tensile test. So that determines the tensile strength, yield strength, and elongation of the material. The impact test specimens, which give the average impact energy information, so there's 5 samples, and these are taken from all weld metal, so that's why these are called all weld metal. So this is the tensile specimen. So that's from the center of the weld, and this picture shows the tensile specimen is made completely from weld metal, which is why it's called an all weld metal tension test specimen. The impact test specimens are also taken from the center of the plate, with the middle of the impact test specimen centered on the middle of the weld. This is to ensure the impact test specimen is testing the impact energy of the weld metal at the center of the weld joint. The point of temperature measurement is also highlighted to ensure consistent preheat and inner pass test temperature readings for all test plates. Preheat and interpass temperatures can have an effect on mechanical properties and must be accurately and correctly monitored. So the mechanical test specimens are machined from the completed test plate. The ends are cut off the test plate. The backing bar is removed. This is the backing bar being removed. The location of the test specimens marked out, and the plate is stamped to identify each individual test specimen. Stamping for the tensile test is done on the end of the plate. Then the plate will be machined to make the individual test pieces. These pictures show the all weld metal tensile specimen being machined. In this picture, you can clearly see the cutout section of weld, the cap passes, and the tensile specimen. This picture is the completion of the machining, and this is the finished all weld metal tensile test specimen. So this is how the tensile test is performed. The test is done using a tensile test machine. This side is where the sample is clamped and then stretched or pulled apart. The side of the tensile machine, on the side of the tensile machine is a large load dial that shows the amount of stress on the test specimen. There is also a roll of paper that plots a continuous chart of the stress on the specimen for reporting purposes, and this is the sample clamped in the tensile machine. The tensile test will determine the yield strength of the weld metal, the tensile strength, and also the elongation. So this is how the test is done. The yield strength, which will always be lower than the tensile strength, is the point at which the material will experience plastic deformation. This means that if you stress a material below its yield point, it will stretch, but when the stress is removed, it will go back to its original shape. These animations show elastic behavior in a material. When the load is added, the material bends, but when the load is removed, the material returns to its original shape. Knowing the yield strength of a material is very important because when the yield strength is exceeded, the structure will be permanently deformed. As an example, the design stress for a steel storage tank under API, American Petroleum Institute, 650 is 2/3 of the yield stress. However, when stress is applied above the yield point but below the tensile strength, and the stress or load is removed, the material will no longer go back to its original shape. In engineering terms, the yield strength is reached when the material shows 0.2% permanent deformation. This movie is showing examples of permanent deformation. The load on the material is above the yield strength so that the shape changes but is below the tensile strength because the material has not broken. These are screen captures from the Tensile Test movie that explains what happens during the tension test. The first picture is the unstressed test specimen. The second picture shows the yield strength has been reached. There is a slight drop in the stress as the material starts to stretch. At this point, the material is no longer elastic and is plastic or permanently deforming. Next, the material starts to work harden as it is being stretched, and more stress is required to keep pulling the test specimen. The ultimate tensile strength is reached at the point where the test specimen starts to have a reduction in area, where the test specimen starts necking. Once necking starts, the strain on the test specimen reduces as the smaller area is easier to stretch, and then the test specimen breaks. Please note, this is for a carbon steel material. Different materials will have different stress-strain curves. Elongation is a measure of the ductility of the weld metal, or how much the weld metal can stretch. So elongation is measured after the tensile test specimen has been broken. To measure elongation, 2 marks are made on the tensile specimen, usually with a permanent marker, before the specimen is placed into the tensile test machine. To make the calculation easy, the gauge marks are placed 50 millimeters apart. After the tensile test has been broken, the 2 halves are put back together and the distance between the 2 dots is measured. As an example, if the original length was 50 millimeters and the final length is 65 millimeters, this means that the specimen has elongated by 15 millimeters, which is 30%. An impact test is also a destructive test, but is different from a tensile test. A tensile test measures the toughness of a test piece under slow loading conditions. An impact test is focused on notch toughness and is a measure of a metal's resistance to brittle or fast fracture in the presence of a flaw or notch and fast loading conditions. Impact properties, also known as Sharpie V-notch, based on the name of the test piece, which uses a 45-degree V-shaped notch, measures the weld metal's toughness or ability to resist stress concentrators such as notches, cracks and voids. The specimen to be tested is machined from the test plate. The size is 10 millimeters square by 55 millimeters long and has a 2 millimeter deep V-shaped notch with a tip radius of 0.25 millimeters machined into the middle of the impact test specimen. For an AWS test plate, 5 impact specimens are broken. The impact values with the lowest value and the highest value are removed. The values of the remaining 3 impact values are averaged to give the result reported on the conformance certificate. Many specifications mention transition temperatures where the fracture behavior changes from ductile to brittle. What the curve shows is that a ductile fracture absorbs a greater amount of energy than a brittle fracture in the same material. Knowing the temperature at which the fracture behavior changes is important when the service temperature of a structure is considered. Ideally in service, a structure should operate at the ductile temperature range. The unbroken specimens are cooled to the required test temperature, soaked at the test temperature for a specified time period, and then moved to the Sharpie machine for impact testing within 5 seconds. The samples in the picture show an unbroken Sharpie impact specimen. An impact specimen can have a ductile failure that will absorb a large amount of energy and can be seen here as the sample that is bent and is not broken into 2 pieces. And an impact specimen that has a brittle failure will absorb a small amount of energy and is broken into 2 pieces. And this is how a impact test is done. So when the impact test is broken, the big hammer hits the specimen on the backside. So it's hitting on the side opposite the notch. So the impact is from this side, opposite the notch. Weld metal hardness is reported on this certificate of conformance, but it is not required for classification. The hardness method reported is HRB, which is the Rockwell Hardness B test that is done by using a 1.6 millimeter diameter steel ball with a load of 100 kilograms to make impressions in the weld metal. The depth of the impression is reported on the certificate of conformance for information only. But hardness can affect the corrosion resistance of the weld metal in hydrogen sulfide environments, which can happen when you're working with sour gas or sour oil, sour type products, which are oil or gas that contains sulfuric acid, sulfur, which becomes sulfuric acid. The chemical analysis provides the information on the deposited weld metal's chemistry, which must meet the requirements of the specification. Ranges of different chemicals are important as they can affect the mechanical properties and arc performance of the electrode. The weld metal chemistry pad must be at least 4 layers in height, and the sample for chemical analysis must be taken at least 6 millimeters above the base metal. This is to ensure there is no dilution between the base metal and the weld metal, to ensure the chemical analysis is of undiluted weld metal. Analysis is done using an optical emission spectrometer that creates sparks on the metal, and the light from the sparks are analysed. So these marks are from the arcing, and this is a optical emission spectrometer machine. The AWS specification has a recommended range for the chemicals that require checking and reporting on a conformance certificate. Big variations in chemical analysis can affect the arc performance of electrodes, which, while the electrode will be within the requirements of the AWS specification, the mechanical results and usability of the electrodes could be different. By using a tighter chemical composition tolerance, it is possible to reduce the amount of variation between different batches of electrodes, which often requires small changes of the welding parameters to maintain consistent arc performance. It should also be remembered that the chemical composition of the flux will also affect arc performance. Manufacturers of electrodes classified to AWS specifications will always have the same chemical composition based on the specification requirements. However, electrodes can operate differently due to the chemical composition of the flux and the tolerance being applied to the AWS chemical composition requirements. Electrodes manufactured with stricter quality control and tighter tolerances will have more consistent arc performance. The Fusible Hydrogen Test, the smallest and largest size of the E7018 electrode to be identified with the optional H designator, in this case the optional designator is H4, shall be tested. The testing must be done in accordance with the appropriate standards. The diffusible hydrogen limits is classed as H4, H8 and H16. This picture shows hydrogen diffusing from weld metal. Hydrogen can come from surface contamination or moisture in electrode coatings. In order for a low hydrogen electrode to be designated as a low moisture absorption with the optional R suffix designator, sufficient electrodes shall be exposed to an environment of 27 degrees C with 80% relative humidity for a period of not less than 9 hours. This is usually done in an environment chamber to ensure correct testing conditions. Having a moisture-resistant flux coating will help to lower weld metal diffusible hydrogen levels. The operating settings is the WPS used for the welding of the test plate. Not every size of every product is tested, and the test results do not need to be published on the certificate for these other sizes. For an E7018 electrode, the 2.5mm and 3.2mm sizes do not require testing. The current and polarity for an E7018 electrode are alternating current and DC electrode positive. For a 4mm 7018 electrode, there must be 2 layers per pass and between 7 to 9 layers for a total of 14 to 18 weld passes. The test joint was welded in 8 layers with 16 passes. Preheat temperature is 105 degrees, C minimum, and the inner pass temperature between 105 to 175 degrees C. The inner pass temperature recorded for the conformance test is 165 degrees C. Fillet weld tests in the vertical and overhead positions are also required for classification. For a 74mm 7018, the fillet weld test is 8mm vertical up and 8mm overhead. A groove weld is for testing of mechanical properties, and the fillet welds are for the testing of the usability, while for an E7018 is classified as an all-position electrode. The result of this testing is the necessary evidence that the product meets the stated classification. The other sizes can be classified providing the electrode has been tested meets the specification requirements. For an E7018 electrode, the specification requires the weld metal to have a minimum yield strength of 58,000 psi and a minimum tensile strength of 70,000 psi. The typical values reported on the certificate of conformance exceed the minimum strengths required. For the Sharpie V-notch impact requirements, the average of the 3 impact specimens after the lowest and highest values are removed must be higher than 20 foot-pounds or 27 joules. However, this is a no single value minimum requirement. If any impact value is less than 20 joules, the whole test fails. If any results of any test fail to meet the requirements, the test shall be repeated twice. That's 2 times. The results of both retests shall meet the minimum requirement. The specimens for retest can be taken from the original test plate or from a new test plate. The weld metal chemistry composition is specified by the AWS specification. This is to ensure that the weld metal is compatible with the base material. This is something to think about. If all E7018 electrodes have the same chemical composition with the same type of flux coating, then all electrodes should weld the same. But electrodes have different arc characteristics and arc performance. And this is because of variations in the chemical composition and also chemicals added to the flux coating. Differences also occur due to thickness of the flux coating. As mentioned at the start of this presentation, an E7018 electrode has a potassium-based low hydrogen flux coating, and that's because potassium is an arc stabilizer that is very important for using an E7018 electrode with alternating current for welding. If there are large variations in the chemical composition, but still within the accepted limits of the AWS specification, experienced welders will notice a difference in arc performance. Depending on manufacturing quality controls, it is possible for welders to notice differences in electrode arc characteristics, which can sometimes affect the procedure parameters between different batches of electrodes. Low hydrogen electrodes are designed so that the diffusible hydrogen content in the deposited weld metal is as low as possible in order to avoid any risk of cold cracking. Hydrogen contributes to delayed weld and/or heat effector zone cracking. Hydrogen combined with high residual stresses and a crack-sensitive microstructure may result in cracking hours or days after the welding has been completed. Low hydrogen electrodes can also be used to reduce the need for preheating.
It's okay, I'll check my thing. Don't worry.
The AWS specification for each type of electrode also specifies the tolerance for diameter, the length of the electrode, the amount of exposed core wire for the electrode hole to the grip, and the information in the electrode identification. Information for packaging, marking of packaging is also included in the AWS specification.
Always fail to force nothing last. I don't know nothing right, so we don't do that. But then when we do the report,
The certificate of conformance that we reviewed during this presentation is based on the AWS specification and an AWS test plate. This will ensure that the electrode conforms with the specification and there is consistency in the performance of the electrode, the mechanical properties, chemistry, and diffusible hydrogen levels. It is very important to remember that this certificate of conformance is based on a test plate welded in the downhand or 1G position. Procedure qualification tests are required to ensure the weld metal meets the requirements of different applications because of different joint designs. The AWS test plate is a single V with backing welded in the 1G position. But there are many different joint designs used on different projects. Some of these are shown here, double-sided joints or different single-sided joints. There is also different welding positions. An AWS test plate is welded in the 1G position. However, on projects, this is not always possible and out-of-position welding is required. Often a project will have a specific specification which has higher requirements due to the application of the project, which includes the service conditions, the location of where the structure will be used, whether the project will be used onshore or offshore. The different specifications can be from the client or a specific specification designed for extreme service. Procedure qualification tests are required to confirm the fitness for purpose. When the manufacturer attaches the AWS specification and classification to the electrode package or places the classification on the product, the manufacturer is certifying that the product meets the requirements of that classification. This method of identification allows the welder to ensure that the proper electrode is being used for the metals to be welded. To make this designation, the manufacturer must conduct the testing specified since AWS does not perform any testing on its own. The results that are reported on the AWS typical certificate of conformance are from the welding tests and the factory analysis, which are completed under a uniform set of conditions and to a rigid set of standards laid out in the specification that covers the consumable group. Classification provides a standard for identifying welding consumables, their minimum tensile strength and usability. An AWS typical certificate is used as proof that the electrode of a given classification meets the minimum requirements for that class. The fabricator can include the certificates for the consumables used for a weldment as part of the documentation of proper construction and proof that an electrode meets the specifications for classifications is the primary use of certificates of conformance.